Thank you for introduction and thank you for a chance to give a talk. My name is Minkyu Kim and today's title is classification of equivariant vector bundles over two sphere. Here, two sphere mean S2. And I will explain for classification of equivariant topological complex vector bundles over two sphere up to equivariant isomorphism. First, we introduce some terminology and notation. G is a compact Lie group, and X is a closed topological manifold carrying topological effective G action. The condition effective means that each non-trivial element of G does not fix the base space X. In my paper, I didn't assume this condition, but in this talk, we assume this condition for simplicity. And next, we define equivariant vector bundle. Complex topological vector bundle E over X is called equivariant vector bundle if E also carries a G action which is comparable with the G action on X, and E is also often called G bundle, just G bundle to stress a Lie group G. Here we introduce a useful notation. Not by EX the isotropy GX representation on the fiber of E at X. I explain for this notation a little bit. This is manifold X, and here is a point X, and an element of G moves this point to GX, and this is EX is usually a fiber vector bundle at at x, and this is the 5 of gx. But since we deal with group action, we give different meaning to this notation. Group element G move EX to EGX. But if G also contained in GX, GX is the isotropy subgroup. Then this point and this point are the same. So these two fibers are equal. So GX preserved EX, and EX becomes a GX representation. We call this representation isotropy representation. So we call this isotropy GX representation by the same notation EX. So we can classify topological complex vector bundles by chunk classes. This is classical. So we expect to classify equivariant vector bundles by equivariant chunk classes. Too many. So, in fact, Hattori and Yoshida proved equivariant line bundles. Line bundles are classified by equivariant chunk classes. This is just a line bundle, but there are no general results. Also, equivariant chunk class and equivariant cohomology are very difficult to calculate. So we do not consider equivariant chunk class. Then what is a substitute for equivariant chunk class? So I answer this question. No. To answer this question by looking at a phenome result. Three results are typical. For 3G action X, G bundles over X and R in one-to-one correspondence with bundles of X quotient G. These are G bundles and these are usual bundle with no action. Here, equivariant vector bundle E is sent to E quotient G. This bundle is over orbit space X quotient G. Because this since this bundle is a usual bundle, this is classified by Chern classes. Also, another result for transitive G action and a point X in X, G bundles over X are in one-to-one correspondence with GX representations. These two results are classical and very easy, trivial, but next one is non-trivial. For X equal to S1 and some 2 points, 2 point X0 and X1, G bundles over X are in one-to-one correspondence with isotropy representations at 2 points. Here mapping is given by this. Through these examples, we choose EX for all X in Chern classes as invariant. Here, EX detects local group action, or local equivariance, and these Chern class detect non-equivariant bundle structure. Non-equivariant means there is no action. you can see there is no invariant to detect global equivariance or global group action. So these two kinds of invariants are not sufficient even in S2. However, these invariants are very useful at least in a low dimension. With these invariants, I have classified equivariant vector bundles of two sphere and two torus and two sphere, two torus, RP2 and Klein butters. And in a totally different approach, I have classified equivariant holomorphic vector bundles over CP1. A classification of equivariant vector bundle is highly dependent on a G action on the base space. So we explain for G action on two sphere. First, we state a classical result. This is classical. Each topological G action on S2 is conjugate to a linear action. This means we may assume that G action is linear. So notation denote this linear action by a representation. By a representation rho from G to O3. Through this representation, GH on R3. So GH on S2. Since
your G is compact, right?
Yeah, right. So the G action on two sphere can be understood by the image of rho. So image of rho G. Rho G is closed subgroup of O3. So we would classify closed subgroups of O3 into three types of two conjugacy. So one. Type 1 are finite or one-dimensional closed subgroups of O3, and type 2 contains two kinds of closed subgroups. But we doesn't explain for type 2 precisely, but just give an example. For example, plus minus identity of O3 is type 2. Is type 2. And last, type 3 are remaining. The remaining, and almost all orient non-preserving subgroups of all three are type 3. In this invariant, I said we choose EX for all X, but you may guess that 3 points of S2. You may guess that considering all EX is unnecessary. When we deal with X equal to S2, we only have to consider EX at 3 points. To explain for this, we give an example. Assume that G action S2 as a tetrahedral group. Then we might regard S2 as a regular tetrahedron. So this is S2. Then here, different color. In this phase, one, two, three. These bold points are these 3 points. I denoted these points D minus 1, D0, D1. We only have to consider isotropic representations at these 3 points. Last, we can state main results. Isomorphism. Precise statements of classification results are a little bit complicated. So we just state 2 isomorphism theorems. First one, if the image rho G is type 1, then 2 equivalent vector bundles E and E prime are isomorphic if and only if their isotropic representations EX and E prime X are isomorphic at 3 points X equal to T minus 1, D0, D1. And there are Chern classes C1E equal to C1E prime. This is isomorphism theorem. We doesn't state isomorphism theorem for type 2. Theorem.
What's the rank of your vector bundle?
Rank?
Yeah.
Any rank.
Okay. You need only first Chern class?
Yes, first Chern class because we deal with space. S2. If rho G is type 3, then 2 equivalent vector bundles E and E prime are isomorphic if and only if their isotropic representations EX and E prime X are isomorphic for 3 points. X equal to D minus 1, D0. This is a second isomorphism theorem.
That's all.
Yeah, that's it. This is the end of this talk. Thank you.
Very much. Questions, please.